talk. So Professor Mallard, can you share your screen? Okay, good. So now the next talk will be by Professor Mariana Mallard from Universidade de Brasília. So Professor, please go ahead.
Okay, thank you very much. I would like to thank the organizers for the kind invitation. It's a pleasure to participate in this very nice conference. And my talk will be about engineering nodal-line semimetals, which are robust, with a very simple method, which is simply by introducing vacancies in your material. And actually, I realized that I was given a full 1 hour to speak. So therefore, I found out that I had time to speak about also a related work, but I cannot seem to change my slide. Are you guys hearing me?
Yes, I think if you click, maybe, and then try to change your slides.
Oh, okay. I was searching for the laser pointer. Maybe it's here. Just a second. Okay, I'll find it at some point. So I actually will use part of my time also to talk about other lattice engineering scheme, which produces nodal point semimetals. And so here in the background, you see the famous Copacabana sidewalk in Rio de Janeiro. And the reason why I use this image here is not just for decoration. It's because this pattern has symmetry, which is, I will talk about that in a few slides. This is a nonsymmorphic symmetry. And this pattern belongs to one of the nonsymmorphic wallpaper groups. I will talk about that in a moment. So I would like to acknowledge my co-workers in the set of works which I'm going to be talking about. So the first two here are my colleagues from the Universidade de Brasília. Then some of the works are done in collaboration with Henrik Johannesson from Gothenburg. Another set of works had the participation of Igor from Buffalo and Wei Chen from Rio. And these are 3 PhD students which are involved in different works, which I'm going to be talking about. So this is just the summary of my talk. So first, I will just remind ourselves about the differences and similarities between quantum and topological phase transitions. Then I'll move on to a very, very brief discussion, or actually a definition of what wallpaper groups are. And then I'll talk about nonsymmorphic symmetries, just to give you a background. And then I'll move on to talk about semimetals and how topology and symmetries play interplay actually to determine the properties of such phase of matter. Then I'll talk about 2 works, or actually a set of works of our group, which we explore this idea of getting nodal lines or nodal point semimetals using lattice engineering schemes. Now we'll show that our theoretical predictions, analytical predictions can be or are verified by DFT calculations done on graphene and borophene. So So here is a very pictorial cartoon of quantum phase transitions, which can be described using the Ginzburg-Landau-Wilson theory, which is based on symmetries. So basically, what you have is that you have some. Oh, sorry. You have some matter, some material, which is characterized by some order parameter, which is here just pictorially represented by these objects, these pyramids. And then the system undergoes spontaneous symmetry breaking, just because the ground state is degenerate. And then it acquires this order parameter, gets ordered, and then this defines the ordered phase of matter. So this whole picture is based then on this Ginzburg-Landau-Wilson theory for quantum phase transitions, is based on the idea of symmetry and spontaneous symmetry breaking. Now, since the 80s or even before that, we started learning about another type of phase transition in matter, which is the topological phase transition, in which the two sides of the material, in the two sides of the phase transition have the same symmetries. But however, there is something that changes, and this is the topological order or the topological features of the material. So here we have the cartoon representing the topological change that is seen in the quantum Hall effect, in which you have an insulator, a regular insulator, which is defined by gapped bulk, and there is a topological change, and then this material becomes an insulator in the bulk, but there are gapless states circulating around the edges of the material, and the ordinary insulator can be mathematically described by a genus, which is mathematically represents the number of holes on a surface, which in this case is 0. So this state is represented or mathematically can be depicted as a sphere, whereas in the topological side, you have a torus with a hole in the middle. So therefore, these two states of matter are topologically distinct, and you have to go a topological phase transition to connect one Hilbert space to the other. Okay, so in both scenarios, you have something. So the phase transition is driven by some parameter of the material, which here I call G. So when G crosses some critical value GC, so you have the phase transition, either be it quantum, just a regular quantum phase transition, or topological. In the quantum phase transition, the symmetry breaking, which happens, is signaled by a continuous change in the order parameter. So you have some function, which is the order parameter, which takes an average, whose average is equal to 0 in the disordered phase, and is a finite number different from 0 in the ordered phase. And this change is continuous across the critical value of the driving parameter. Whereas in a topological phase transition, the transition is determined by a discontinuous change in something which is not an order parameter because it's not connected to a symmetry, but it's a topological invariant, which takes on, that's therefore the name invariant, it's invariant within each phase. So in the trivial phase, it's 0 everywhere. In the topological phase, it is non-zero, but it has a fixed value. So there is a discontinuous change in the topological invariant across the transition point. Okay, now I'm going to switch gears to a different subject, which I just want to briefly define wallpaper groups. Wallpaper groups, well, there are 17 crystallographic groups in 2 dimensions, only 17 as opposed to more than 200 in 3 dimensions. So in 2 dimensions, you just have 17 crystallographic groups, which are called wallpaper groups. And here you have them. So these are some cartoons which illustrate the symmetries of the patterns which have the symmetries of each one of the 17 groups of the wallpaper groups, which are the crystallographic groups in 2 dimensions. These groups are characterized by 4 symmetry transformations, so translations, rotations, and reflections, which are symmetric spatial symmetries. And then you have glide planes, which are non-symmetric spatial symmetries, and I will talk about that in the next slide, which is the meaning of this name non-symmetric spatial symmetry. And the non-symmetric groups, there are only, I think I missed to include that slide. So there are only 4 non-symmetric wallpaper groups out of the 17 ones. So what are these non-symmetric symmetries? So in 2 and 3 dimensions, you have one symmetric symmetry or transformation, which is called the glide plane, which here I'm going to illustrate using this figure of right and left feet. So this pattern has, so the unit cell of this lattice, so to speak, is given by 1 left and 1 right foot. And then this pattern has what's called the glide plane, which is the combination of a reflection plane and a non-primitive translation. What is a non-primitive translation? It's a translation of a fraction of the unit cell. So, which means that in the case of this picture here, if you reflect the pattern with respect to this line, then you get this. So this is the original pattern. So upon reflection, it's transformed to this dark green pattern. But you see that you do not recover the original pattern, which is here drawn in light green. So you need to translate by half of the unit cell in this case in order to recover the original pattern. So therefore, this system is invariant under this glide plane, which in this case involves a translation, a non-primitive translation of half of the unit cell. There is also another non-symmetric symmetry, which is present only in 3D materials, 3D lattices, which is the so-called screw axis, which here I'm going to represent using this pattern of, oh, now I finally found the laser point. So and here I'm going to represent the screw axis using this pattern of left hand with palm facing up and down, like so. And you see that here the unit cell contains 2 such objects. And this system or this pattern is invariant under, so what is a screw axis is n-fold rotation axis, which in this case of this picture here is a 2-fold rotation axis. Followed by a non-primitive translation. So if you rotate the pattern with respect to this axis here, so you get this pattern here, which is drawn with the dark lines. But now again, you need to translate along the axis by half of the unit cell. So this is what's called a screw axis in 3-dimensional structure. Okay, then I'm going to switch to a third topic, which is, so I'm going to talk about generically about semimetals and how topology and symmetries are come together in order to define or determine the properties of the band structure of such materials, semimetals. So we know that there are basically 3 different types of semimetals, Dirac semimetal, Weil semimetal, and Jens has talked about these 2 types of semimetals in his talk, mostly focusing on Weil semimetals, which are distinct from Dirac semimetals in that they have 2 band touching points, where here you have a four-fold degenerate band touching point in direct semimetals. So this degeneracy split, right? So when you break time reversal symmetry or inversion symmetry, and you get these two separated in momentum space band touching points, which are the vial cones. There is a third type of semi-metal, which is the nodal-line semi-metal, which is when the valence and conduction band touch or cross, not at points in the Brillouin zone, but along whole lines in the Brillouin zone, which might be closed, forming closed loops, or open lines. Typically, you find that around these band touching points or lines, the dispersion is linear, right? So this is the origin in the case of points of the massless fermions that you have around the linear, the band touching points with linear dispersion. And okay, so in most of my talk, or actually in the fourth fraction of my talk, I will be mostly concerned with nodal-line semi-metals, which are interesting because they might support very interesting topological edge states. They typically are associated with flat bands with very large density of states, which can be used for various technological applications. They can be used as precursors of high TC superconductors. They can be used also to generate non-trivial magnetism and a plethora of other interesting phenomena. Okay. In general, here I'm using the picture of a nodal-line semi-metal, but this slide is generic, which has to do with the fact that a band touching, when bands cross or touch each other, be it along a line or just at isolated points, this band crossing, which is a violation, you could say, of Wigner theorem, which states that bands generically avoid each other. So when such a band crossing occurs, two things can occur if you submit this degeneracy to perturbations. Perturbations might split the degeneracy. In this case, the degeneracy is called accidental because any small perturbation will split the degeneracy. And this happens when this degeneracy is associated or comes along with spatial symmetries which are symmetric. Therefore, they do not involve fractional translation, so just regular point group symmetries. And non-spatial symmetries such as time reversal symmetry, particle hole symmetry, or chiral symmetry. Or the band degeneracy is enforced by the symmetry, by underlying symmetries of your material, in which case any arbitrarily large perturbation that preserves the symmetry will not destroy the degeneracy. So we say that, therefore, that this degeneracy is enforced by the symmetry or symmetry-enforced, and this happens in the presence of non-symmetric symmetries, which are glide planes or screw axes, as I have defined before, or actually presented before. So now, suppose you are interested in robust semi-metals, which survive strong perturbations, and this is important for applications for obvious reasons. Then you want to focus on symmetry-enforced kinds of semi-metals, and then you can go and find intrinsically non-symmetric materials, right? So the problem with this path is that this kind of materials are normally chemically complicated because typically the unit cell involves at least 2 types of different atoms. So these are not pure materials, these are compounds. And also they can be very structurally complicated. And here I just give you 4 examples of materials that have nonsymmorphic symmetries. And these are all 3-dimensional materials. And as you can see, they involve more than 1 type of atom and have quite not very simple structures. And this is the path that we propose, you just get a very simple symmetric material that can be even a monoatomic and doesn't even have to be 3 dimensions. And actually we test this idea with 2-dimensional lattices and it works, as you will see. And we make it nonsymmorphic by lattice engineering. Okay, so to show how this idea, I will show one realization of this idea, but let us just go back to the case of accidental vial semi-metal, which is a 3-dimensional material. So we know that there are 2 vial cones, and these are accidental because they demand tuning parameters, as Jens explained. And so they have a number of features. One is that they carry opposite topological charge. And as you vary a parameter of your material, of your Hamiltonian, these 2 points can move in the Brillouin zone. But eventually, if you just go on with this perturbation forever, there will be some critical value of this parameter in which these 2 points will merge and the 2 opposite topological charges will annihilate each other. And then the band touching point will be gapped out and then you lose the semi-metal, right? So in this sense, we say that this kind of system is topologically protected, but only locally, because this process exists within a finite regime of parameter in your momentum parameter space. Okay, now we have found that in 1D, it's possible to induce band degeneracies which are vial-like. They're not vial cones because, first of all, this is a 1D Brillouin zone, and also there are some other differences, as I will talk about next. But these nodes, different from vial cones, which are accidental, these nodes are symmetry-enforced. So here in this animation, you see the band structure of the model, which is just a simplified 4-band effective model. And the middle bands, they touch at these points in the Brillouin zone. And you see that these points move in the Brillouin zone as one of the parameters here. In this case, it's theta, and I will define this parameter in a moment. So it's varying. So you see that as this parameter varies, the band touching points, they move in the Brillouin zone, but they never come on top of each other and gap out. So these 2 points, these 2 band touching points, they are time reversal symmetric, but differently from vial cones, they carry the same topological invariant. They move, as we see in the animation here. However, they cannot merge and be gapped out by any parameter variation in the Hamiltonian. Here, I'm just showing the variation of this parameter theta, but if I vary the other parameters which exist in my Hamiltonian, the situation is the same. So the points move, but cannot come on top of each other and annihilate. And this means that these 2 band touching points are globally, they are topologically protected by this topological charge. And moreover, they are globally topologically protected. And this has to do with the symmetry of the chain, right? So before I move on to the specifics of the model, let me just show you this picture, which represents the position of the two points, the two band touching points in the Brillouin zone. So K plus, K minus are respectively the right and left band touching points. And this is these are two parameters of my model. So as they vary in the entire range of, in their entire domain of these parameters, you see that the band touching points, they can even get very close, but somehow they repel each other, so that when they get close, they eventually start to repel and get apart, move apart from each other. So you see this for both cases, for the variation of these two parameters here. Okay, so this kind of situation appears when you write down a tight binding model, which here I will not show the equation, not to bore you with very long formulas, but it's just a simple tight binding model which contains spin orbit coupling of two types, uniform Dresselhaus, so it has hopping, so just normal uniform hopping, and then it has uniform Dresselhaus spin orbit coupling and uniform Rashba spin orbit coupling, but also a spatially periodic contribution to the Rashba spin orbit coupling. So here is just a cartoon of such a lattice in 1D, which is it's a one-dimensional model. So you have a unit cell, which is large in the sense that it contains more than just one site. So here, generically, it can contain R. Let's say it contains R sites. And the reason for that is because you have a larger wavelength, which is defined by the spatial periodicity of the Rashba spin orbit coupling, and that enlarges your unit cell to contain the long wavelength of your Hamiltonian or of your system. So you have spin, so it's a spinful 1D lattice, and there are two types of processes: spin conserving hoppings, which are parameterized by this alpha parameters. So this alpha plus is hopping for spin up, this alpha minus is hopping for spin down, and betas are the hoppings which change the spin or flip the spin in your along the chain. So this, as I said, the size of the unit cell is the period of the Rashba, the spatially periodic Rashba contribution. So these alphas and betas are parameterized by microscopic parameters gamma effective, theta, and phi. Gamma effective is just, so if you draw the plane in parameter space defined by the intensity of the Dresselhaus spin orbit coupling and the intensity of the Rashba spin orbit coupling, gamma effective is this radius on the plane, and theta, which is the second parameter here, is just the arc tangent of gamma d divided by gamma r. And then you have phi. This phi parameters, as you're gonna see, is quite important, and it is the phase shift between the internal periodicity of your lattice, so the lattice spacing, and the periodicity of the Rashba spin orbit coupling. So here you just have your lattice sites with the uniform lattice spacing, and then you have a long wavelength, which is the period of the Rashba spin orbit coupling. And here I'm drawing just the case where they are in phase, so they have a phase difference of 0 or 2 pi, but generically they do not have to be in phase; they can be out of phase, as drawn here. So this phi parameter is the parameter that takes this into account. Now let me just show you this equation, because it's important to conceptualize some of the results. And this is the 4-band, so not this case, it's not 4-band, it's I have R or 2 times R bands, because there are R sites and each site can carry spin up, can host spin up or spin down. So this is a 2 times R band Hamiltonian to the matrix, 2R times 2R matrix. which it has this form. So this is my block Hamiltonian in momentum space. So you see that these blocks are 0, and then the off-diagonal blocks are the blocks which carry the non-zero elements, which are given by this matrix Q. And I can write down this matrix in this generic form, and this A1, A2, A3 up to AR are 2x2 matrices, which inside this matrix, I have this alphas and betas, which are the spin conserving and spin flipping hoppings respectively. So this is just how you can write your Hamiltonian in momentum space from Fourier transforming the tight binding Hamiltonian. This is all very straightforward. And it turns out that this matrix, this Bloch matrix, has 3 symmetries, 3 non-spatial symmetries, which are chiral symmetry, time reversal symmetry, and particle hole symmetry, which, as we know, are the non-spatial symmetries that define fold-way classification of topological matter. So in this case, I have all the 3 symmetries for this matrix here with chiral matrix, with the chiral transformation matrix given just by this formula. The time reversal symmetry is matrix is given like so, and the particle hole symmetry is such. And because of the presence of all the 3 symmetries, and since S squares to 1, T squares to -1, and C squares to 1, to -1, it means that my Hamiltonian belongs to class C2 of the 10-fold way. Well, in class C2 of the 10-fold way in 1 dimension, which is my case, the system is topological, and moreover, it is described by a topological invariant called winding number, which when the bands are gapped, can be defined as the number of times that the determinant of this matrix Q. So just remind ourselves that Q is the matrix that sits in the off-diagonal corner of the Bloch Hamiltonian. So this is a complex number. So it winds on the complex plane as my parameter, my momentum K, goes from -pi to pi across the Brillouin zone. So when this happens, this number will wind in the complex, on the complex plane, because pi and -pi are the same value because of periodicity of Brillouin zone. So it goes, so this number goes back to itself. And while doing that, and it can or cannot enclose the origin. In this case, it's enclosing the origin, which means that the winding number is 1 and actually can go around the origin an integer number of times. So the winding number can be 1 or 2 or any integer, and which determines that the system is topological. But if this loop does not enclose the origin, then the winding number is 0, and therefore the system is in a topologically trivial phase. Well, that works very well for a gapped spectrum, but sometimes, as we will see, for a certain value of this parameter phi, in fact, for this particular value of phi, which is pi over 4, the system becomes, the spectrum becomes gapless, which means that this loop will cross just through the origin of the complex plane. And in this case, the winding number is ill-defined because you cannot say that it encloses or it doesn't enclose the origin because it's cutting through the origin. For this kind of situation, we have to define a modified version of a winding number, which is the following. So you take your parameter, momentum space. K is momentum and phi is this parameter of your Hamiltonian. And this is the gap closing point, which is some value of K in along the momentum axis and this particular value of phi. And this is when the gap closes. So you enclose this gap closing point, defining a small loop around that point. And then you ask yourself, how does this number, determinant of this matrix, winds on the complex plane as you go around the loop? And then you find that for this case, this is a well-defined winding number. So the number winds on the complex plane and without cutting through the origin, because of course you are avoiding that point. And then we compute the winding number for the gapped regime of our Hamiltonian, and also the modified winding number for the gapless regime of our model. And I will just skip the formula. I'll just skip the algebra. And this, what you're seeing now, is the result. So I have a three-dimensional phase diagram where the empty regions, the empty chunks, are defined by having winding number equals 0. So these are the gapped insulators, or rather the gapped trivial insulators, and where the dotted chunks are for the are defined by winding number equals 2, which means that you have a trivial topological insulator. And these trivial and topological insulators, they are separated by critical surfaces, which are surfaces where the gap closes or where the bands touch. And what you have is that there is a plane defined by phi equals 0.25 phi, and also there are some curved surfaces which are accidental surfaces in that. How can I say that? Well, first I have to say that there is a symmetry associated to this particular value of phi, whereas there is no special symmetries associated to this curved surfaces. So, which means that here the gap is closing just accidentally, right? Okay, so just continue. We compute the modified winding number for all of these gap closing surfaces, and we find three situations: -1, 0, and 1, which are depicted in blue, yellow, and orange, as you can see here. And you see that the point where the modified winding, the points where the modified winding number is equal to 0 are these multi-critical lines where these critical surfaces intersect each other. And also here you can see the band structure for all the three different sections of winding number. For winding number -1, so you see that the bands touch at 2 points in the Brillouin zone, and if you compute the topological invariant, you get -1 for both. Whereas in the orange sections, you get +1 for both. And as I said, in the along the lines where the critical surfaces intersect each other, the winding number at the points where the bands touch is equal to 0. Also, which is important, is that particularly for this value of phi, the system acquires an extra symmetry, which is a mirror point, which is here. So you see that the values of the hoppings are mirrored, are reflected on each other with respect to this point. So the bonds, as you can see here, have a mirror symmetry, or are mirror symmetric with respect to this point. And this symmetry is off-centered, which means that this mirror point is not in the center of the unit cell. It's shifted from the center of the unit cell. And the consequence of that is that the matrix which describes this mirror symmetry becomes k-dependent. And this is a feature of a nonsymmorphic symmetry, right? So the matrix is k-dependent, different from normal reflection, where you can describe the matrix just by some kind of parity matrix, like sigma x, for example. Here, you need k dependence in order to describe the matrix, and this is rooted in the fact that the mirror point is shifted from the center of the unit cell. And this is what's in the basis or in the root of the enforcement of these band touching points here. So they must be there because of the form of the mirror matrix. And in this case, because the matrix is not associated to any specific k point in momentum space, it's rather there is one such matrix for every and each k point. Another consequence of that is that for the point, the nodal points can move in Brillouin zone. They are not pinned at a so-called high symmetry point, because all the points are high symmetry points. So this is what enables these points to move in symmetry in momentum space, emulating vial cones. However, they are symmetry-enforced. They can, unlike vial cones, they cannot be gapped out. Okay, so next I would like to move to another topic, which is the last part of my talk. So if you have some questions to ask, maybe it's a good time, because I'm going to move to a different subject. Yes?
Yes, I have a question about this lattice engineering. It can be generalized to another direction, because your schematic is just 1D, right? So
yes.
If you create something like in 2D, for example, in this thinking in this connection, it is possible?
Good question. I think so. What is the key ingredient here is that there is two periodicities. One is the crystalline period, which is the lattice spacing, and another is an engineered periodicity, which in this case we implement as a Rashba spin orbit coupling, which is periodic in space, with a wavelength that is larger than the wavelength of the crystal, so this is the key ingredient. So you have these two periodicities and you have a mismatch between them. So remember that this phi is the phase shift between these two periods. In real life, how can you get a spin orbit coupling or a Rashba spin orbit coupling that is modulated in space? Well, we know that Rashba spin orbit coupling is sensitive to external electric field. So if you just apply a periodic electric field, then your Rashba spin orbit coupling will inherit the same periodicity of the externally applied field. So in principle, I would imagine that you can do this in 2D, that you could do this in 1D or 2D or even 3D, right? So, and I should mention that another key ingredient is that it's not only Rashba spin orbit coupling that is given this phase diagram. It's also important that you have Dresselhaus spin orbit coupling, and it's actually the interplay between the Rashba spin, the spatially modulated Rashba, and the uniform Dresselhaus that gives you this spin flipping hoppings. So if you work out the algebra, you find that these spin flipping hoppings, which are responsible for this phase diagram, they depend, there is a factor in front which depends on the product of the Rashba and the Dresselhaus spin orbit coupling intensities. So these are the ingredients that I think that in 2D you could. So what I want to say is that nothing in this proposal relies really on the model being one-dimensional. It's just the one very easy model to work out.
Okay, thank you.
Okay. So maybe now, yes, I wanted to show to you that also you can use lattice engineering. In this case, I'm going to use vacancy engineering. So basically, I'm going to poke some holes on a two-dimensional lattice, and that will allow the formation under certain circumstances, which I'm going to describe, that allow the formation of nodal-line semimetals, which are robust under perturbations because they are also symmetry-enforced. And here I show you two types of two-dimensional lattices: graphene, which is the most studied two-dimensional material, and also similar material, which is borophene, which has a very similar structure to graphene, except that it has boron atoms also at the center of the hexagons. And both these structures have symmetric symmetries, which are the reflection planes in along both directions here, and inversion point. In this case, the inversion point is implied by the presence of the two reflection planes. And the presence of these symmetries entails that the spectrum has the famous Dirac cones, where the conduction and valence bands touch linearly at points in the Brillouin zone. However, this band touching, this Dirac cone is not robust to perturbations. So in principle, it's perturbations like, for example, spin-orbit coupling open up a gap. And so therefore destroying this degeneracy. And what happens when you introduce some holes or vacancies on your structure for borophene or graphene is that one of the reflection planes here R2 is replaced by a glide plane, and in graphene, this R1 is replaced by a glide plane when you remove some of the boron or carbon atoms. And the result of that is that the bands now touch along the lines in the Brillouin zone, and not only that, these are robust. Studied some variations of this structure for borophene. So this is B10 borophene because the unit cell has 10 atoms in it, but also it works for larger unit cells. So here you have the situation for B16 with 16 atoms in the unit cell. And if you proceed with certain adding certain number of atoms in the unit cell, you go on and generate a sequence of similar structures which all have the same symmetries, and in particular the desired glide plane. And for graphene, here you have the C10. We have also studied the C44, which is a structure with a much larger unit cell, but which also has the same type of symmetry. Now let's understand, on the basis of a very simple and effective model, what's going on in this kind of structure here. So let's take, for example, B10, which is this one. So if you look at the unit cell, you see that it's characterized, or actually rather, if you look at the whole structure, you see that there is this zigzag kind of pattern which is formed between hollowed hexagons and filled stripes, separated the stripes of hollow hexagons. So basically, the minimal defining feature of this structure can be represented by a very simple kind of lattice where you have these objects, which here I represent as squares, which are shifted along this direction, forming this zigzag pattern of two types of objects, here blue and white squares. In this kind of minimal lattice, this kind of minimal lattice, which has the same, exactly the same symmetries as the real material, can be described by a rather simple and easy unit cell, which contains only 4 objects, as you can see here. And therefore, the effective Hamiltonian is a 2-dimensional 4-band Hamiltonian instead of for example, for B10. So since you have 10 atoms in the unit cell, 4 orbitals per atom, and spin, you would have what, 80 bands. So here you have just a 4-band effective model, which contains all the basic ingredients, which are the desired symmetries. So if you just look at the invariance relation that this 4x4 Bloch Hamiltonian has to obey so that it's invariant under a glide plane transformation, this is the relation. So this is just, it follows from the theory. So this is the 4x4 matrix that describes the glide plane transformation on this simplified toy lattice. And then when the Bloch Hamiltonian is sandwiched in the middle of the glide plane matrix and its inverse, so it has to go back to itself, except that this ky momentum is flipped. And therefore, it means that if you take an eigen state of your Bloch Hamiltonian, this guy here, where alpha here is a band index, which in this case is 1, 2, 3, and 4, because I just have 4 bands in my toy model. So if you apply the glide plane transformation, you transform this k minus ky eigenstate to a plus ky eigenstate, and also you can go to a different band. This transformation is depicted here. So you transform the positive ky eigenspace of your Hamiltonian into the negative ky eigenspace, and you might also change the band when, so alpha goes to alpha prime. And there is a factor, a phase factor in front, which might depend on momentum and the bands, and okay. Now, what happens if ky is either 0 or at the edges of the Brillouin zone, plus or minus pi? Well, in this case, this relation becomes a commutator, which is equal 0, and which means that obviously now the Hamiltonian and the glide plane matrix share a common set of eigenstates, and in particular, so this is the equation of the eigenstate and eigenvalue equation for G in this particular case where ky is 0 or plus minus pi. So you see now that the state goes back, is mapped back onto itself, and this is the eigenvalue. Well, it's actually pretty easy to compute this matrix for a 4x4 lattice, for a lattice with a simplified lattice with a unit cell of which has only 4 objects in it. So this is the matrix. So this little g here is the 2x2 matrix, which has this simple formula. And so this is the form of the 4x4 matrix, which you can diagonalize by hand. And these are the eigenvalues. They are doubly degenerate. You have this 1, 3, doubly degenerate eigenvalue, and the other one is the same, but with minus in front of it. And what happens is, if you look at how these eigenvalues vary on the complex plane, as this parameter kx swipes the one edge of the Brillouin zone from minus pi to pi, the eigenvalues, they go around half of unit circle. So, for example, the plus eigenvalue, this one, goes from minus I to I, passing through 1, and the other one goes in the other direction, along the other half of the unit circle. And then if you look at the eigenstates at the end, at the two ends of these two purple and green trajectories, these are the eigenstates which are associated to these extreme points. And if you just work out the algebra, you find that this will lead to the following fact, that the eigenvalues of the Bloch Hamiltonian, or the eigenenergies associated to these eigenstates, they will have to cross in pairs for some value of kx. This value is generic, can be any value, but they will have to cross in pairs for some value of kx, like represented here in this cartoon. Okay, very good. So this by itself guarantees that there are band touching points, or actually rather a pair of band touching points for whenever ky is ky bar. Ky bar is either 0 or plus minus pi. And that's enough. That's what we want to prove. And this we can prove even without prescribing any form for this Hamiltonian. This could be any Hamiltonian as long as it obeys this invariance relation. It follows that its spectrum, the bands, must touch in pairs when ky is 0 or plus minus pi. Let's test this idea for one particular such Hamiltonian. So let's take the simplest tight binding Bloch Hamiltonian, whose entries are represented here as epsilon 1, 1, 1 by 4 matrix. And generically, if it's just a tight binding Hamiltonian with nearest neighbor hopping, it will contain all these terms here, where T and T star are represent the hoppings within the unit cell. So any hopping from site 1, 1 to 2, 1 to 2, 1 to 3, 1 to 4, and so on, but within the unit cell. And these parameters U here represent hoppings between neighboring unit cells, but along the horizontal direction, the mx direction. The V hoppings represent the hoppings along the vertical direction, and W are for the hoppings along the diagonal. Very good. This is the most generic tight binding Hamiltonian that one can write in this kind of for this kind of lattice structure. And now I just go on and impose that this generic 4x4 matrix must obey the invariance relations with the glide plane matrix, also with the inversion point, because remember, there is also inversion point. Let me just remind you of that fact. So there is an inversion point on the glide plane here. So this is also a symmetry that must be satisfied. And then also I'm going to impose time reversal symmetry, because I'm actually not imposing. It has time reversal symmetry because I don't have any thing in my Hamiltonian that breaks time reversal symmetry. Nothing is magnetic. So I can compute all of these matrices G, which I have already shown to you. And then I go on and compute I and T, and for T is just the identity because I don't, this is a spinless model. And the matrix for the inversion point is this one. And then I just go on and enforce that H must satisfy this invariance relations with such matrices. And when I do that, what I will acquire are the constraints that these invariance relations impose on these numbers epsilon and m of kx and ky. And then I just go on, diagonalize my Hamiltonian, and that's what I get. I'm going to show to you what happens in steps. If I just...
Professor, sorry to interrupt you, but we're a bit over time, so if you can start to wrap up.
Okay, I'm coming towards the end of my talk, okay, so let me just wrap up. So if you just impose G, which is the glide plane symmetry, you see that your 4 bands, as we have already shown algebraically, will have to touch whenever k, y is 0 or pi. And then here I'm just showing to you the projection of these band touching points on top of the kx, ky plane. And you see that they fall on top, as I said, of the ky 0 or ky equals pi or minus pi. Very good. Now I add inversion point. And just to sum up, what happens is that inversion point pushes all the 4 band touching points to kx equals pi. If I now go and add time reversal symmetry, every pair of band touching points are connected by lines which run parallel to the ky axis, and also accidentally, and these are symmetry-enforced lines, but accidentally there is also a line that appears, a band touching line, which appears for kx equals 0, which is immediately destroyed when I introduce anisotropy in my hopping parameters. And why am I doing that? Well, I'm doing that because when I introduce vacancies, one side effect of introducing vacancies is that you break the isotropy of your hopping. So your hopping will be different in different directions because there are some directions where there are holes because of the vacancies. And therefore you have anisotropy. What it does is that, first of all, it destroys this band touching line, which shows that it's accidental, but importantly, these 2 band touching lines, they will survive any anisotropic situation. And also as anisotropy will induce some generic, in the sense that they can be located anywhere inside the Brillouin zone, band touching lines between the middle bands, so the green and blue bands here. So if you change, for example, the anisotropic parameters, you can make this accidental nodal-line move and change shape in the Brillouin zone, which might be very interesting for applications. Now I'm very briefly going to show you some DFT results for borophene, which show that our theoretical and analytical results are confirmed. So this is the band structure for B10. Sorry, somehow the unit cell is not showing, but so this is the band structure for B10. So you see that every 2 bands stick together along this direction XV in the Brillouin zone. And this direction XV in the Brillouin zone is exactly the predicted direction, which is Kx equals pi or minus pi. So if you see the projection of these sticking bands on the Kx, Ky plane, you see that this golden line here represents the vanishing of the gap between the bands. So you see that they are exactly where they should, as predicted by the analytical results. And as I told you, also there are some generic accidental nodal lines inside the Brillouin zone, which have very beautiful shapes. You see that if you apply spin-orbit coupling, of course, the nodal lines at the edges of the Brillouin zone, they survive as they must because they are symmetry-enforced. However, surprisingly, the accidental ones, although they split because spin-orbit coupling breaks spin degeneracy of the bands, they split, but they survive under very, very strong spin-orbit coupling, which is quite surprising. And we actually understand that on the grounds that these accidental nodal lines in the inside the Brillouin zone are being created by anisotropy. And anisotropy is a structural feature of your material. So it's not easy to break it. It's not easy to make the material isotropic again when you introduce any perturbation, for example, spin orbit coupling. Rather, it's probable that you are going to enhance anisotropy when you introduce a perturbation. So you see that these accidental nodal lines, however accidental, they are unusually robust, and we trace back this unusual robustness to anisotropy. And these are the results for another borophene, the B16, and we see the similar, the same features, so symmetry-enforced nodal lines at the edges of the Brillouin zone, and accidental nodal lines, which are unusually robust inside the Brillouin zone. And these are the results for graphene. We see the same features, so I'm just going to flash these last slides. Also, we have computed for graphene the DOS, the density of states close to the Fermi level, and we see that this kind of vacancy-engineered structures have an enhanced density of states close to the Fermi level, which might be very also relevant for applications. These are the results for another type of graphene, the C44. In this case, you have two glide planes, which means that you have 4 nodal lines, one pair for each edge of the Brillouin zone. So in the end, you have a nodal loop circling the entire Brillouin zone, which is also interesting. And I'm going to skip the tiding binding results for graphene because we don't have more time. So these are my final remarks. So in this talk, we have seen how an off-centered chain obtained from an external modulation of a spin orbit coupling hosts a pair of time reversal related and symmetry-enforced nodal points, which, despite being symmetry-enforced, can move in the Brillouin zone, unlike viol cones, which move in the Brillouin zone, but they are eventually gapped out by perturbations. And we have also seen that a nonsymmorphic two-dimensional material created from vacancies can host symmetry-enforced nodal lines at the edges of the Brillouin zone, but also unusually robust accidental nodal lines in the interior of the Brillouin zone due to anisotropy, which is induced by the presence of vacancies. We have confirmed these analytical predictions by DFT calculations with borophene and graphene. And I would like to point out that these proposals are only based on symmetries. They do not rely on any chemical or sample or any microscopic details of the materials. So therefore, that can be utilized or applied to other types of materials as well, besides the ones that we have explored. And as outlooks, I would like to, in the future, explore the emergence of topological edge states in such semi-metals, symmetry-enforced semi-metals, topological superconductivity, and see how proximity effects can generate non-trivial magnetism to design other properties in this kind of materials. So basically, we see that lattice engineering can be very useful to obtain topological and robust semi-metallic phases. And this opens a new path to material designs of topological semi-metals. With that, I thank you all for your attention. And if I might have a few more minutes, I would gladly accept some questions.
Okay, so thank you, Professor Mallard. So we are running late, but we will have time for one quick question, if there is one. Okay, so I
can't hear.
Oh. Okay, so I had a quick question, which is you studied a lot of the non-symmorphic symmetries for two-dimensional, and so if you move up in three-dimensional, you have more non-symmorphic groups. but you also have this phenomena of nodal knots, which seems to appear. Have you by any chance either explored a higher dimensional, three-dimensional systems, non-symmetric systems, and seen by any case nodal knot semimetals that arise with these symmetries?
We haven't. In 3 dimensions, people have found compounds, and I have shown a few instances which are non-symmetric, and they have studied the semi-metallic phase in these materials. But the philosophy of our proposal is that you can generate non-symmetricity in simpler materials and even one-dimensional structures just by lattice engineering. In principle, you could do the same kind of scheme in 3 dimensions. So, for example, you can also generate non-symmetric symmetries by poking holes in 3-dimensional crystals. But we wanted to see if that idea worked first with even simpler structures, and we have proved that it does.
Okay, perfect. Thank you. And with that, let's thank again Professor Mallard, and we'll
thank you very much.
The next talk.